doing? I hope everyone is doing good and great. I'm Mahesh, your physics teacher, and you're watching me on SMR Online Physics. If you're new to this channel, do not forget to like and subscribe my channel for more interesting classes on physics. And if you are a regular follower and viewer of my channel, yes, you know what's going on. In the last class, I discussed about refraction of light. And today, we will discuss about the laws of refraction, the very important Snell's law, and the concept of refractive index. Hope we have lots of fun together in today's class. And at the same time, should not forget the main motto, physics should remain a fun to learn. Okay? Hope we have a good time. So let's get started. The topic of today's class is the laws of refraction of light. So take it easy, very simple. I'll keep it simple and make it simple for you as much as possible for sure. Okay? So we know exactly from my previous classes, or definitely you might have learned somewhere else, what is exactly refraction of light. Alright? So generally as a ray diagram, we follow this. We try to show an interface. This is our interface, a separating layer between the two transparent mediums, and yes, a ray of light incident obliquely from one transparent medium moving into another transparent medium does not tend to go exactly straight. So this is my reference line passing right through the point of incidence, that is O in this diagram. It doesn't go really straight in its own path, but we will show it as a reference line. The intended path should have been that. Now it depends upon what we call as the optical densities of the medium. So if I name it like the first medium is this air and the second medium is clean water, then definitely the ray of light won't be going straight or won't be bending away from normal as we say, but rather in this case it will be bending towards the normal. This is how it looks like. So the students who know this concept or who have visited and seen my previous class on this topic definitely knows the answer why it's happening so. We will say water is optically denser than air medium, so hence when a ray of light passes from rarer to optically denser medium, the speed of light in the denser medium decreases. So the decrease along with a change in the direction of propagation is shown in the ray diagram, something as this. So the angle between the incident ray and the normal is called angle of incidence. The angle between the normal and the refracted ray is called angle of refraction. And the angle between the original direction of the incident ray and the actual refracted ray, this tiny bit of angle is called as angle of deviation, which I have already discussed in my previous class. Alright? If you haven't watched my previous class, please go watch it first, then come back to this for better clarity of the concept. So the first law of refraction states that, let me just put in a name here, PO standing for incident ray, O the point of incidence, N dash standing for normal, OR standing for refracted ray of light. So the first law states the incident ray, the normal at the interface separating the two media, and the refracted ray all lie in the same plane. I think most of you immediately connect with this statement of the first law because it sounds very similar to the first law of reflection of light. But here the key word which has been changed is there is a refracted ray coming in place of reflected ray. What does this law say? The point is very simple. Any ray of light which is incident obliquely from one transparent medium onto the interface separating the second medium, the incident ray, the normal passing through the point of incidence, and the refracted ray all lie in the same plane. So if you ask me where is the plane right now, all the three are lying on the plane of this vertical board. That's it. If you're drawing it on the plane of the page, then all the three should be lying on the plane of the page. What if there is any hint of doubt? I mean to say, as the incident ray of light strikes the interface, you can just follow my palm. After striking over here, the refracted ray won't be coming out of the plane. That is what the first law exactly says, right? Now moving on to the second law, which is very, very important. Very, very important. It was given by a Dutch scientist who proved it for the first time mathematically. His name was Willebrord Snell'S. Just to name him, yeah, he is Willebrord Snell'S, and today the second law is also famously known by his name, Snell's Law of Refraction. Now what is Snell's Law of Refraction? Let me just tell you, excuse me. Snell's Law of Refraction states that, now it's related with the angles concept. It says the ratio of sine angle of incidence to the sine angle of refraction is always a constant. Is always a constant for a given pair of media. Let me just finish up writing here. And for a given color of light. Yeah, when I'm writing on the board, it sounds a lengthy statement. The idea is absolutely simple. So what is the law actually stating up? It says that the ratio of the sine angle of incidence. I need to take this trigonometric ratio of sine for the angle of incidence and measure it with respect to the sine angle of refraction for any given pair of media, and the color of light should be constant. Then the ratio is always found to be constant. So it means that mathematically the law will be sounding something like this. Sine angle of I by sine angle of R is equals to constant. That is what the law mathematically sounds. Okay? Sine of I by sine of R is constant. But my dear students, please focus that it is always a constant only when the two conditions are fulfilled. For a given pair of media and for given color of light. And by the way, what is that constant? Does it have a name for itself? Absolutely yes. So what is that constant and what it is going to talk about this given transparent media? Let me discuss about it. This is the statement of Snell's law. You can just note it down, right? So now I need some space, so I clean it up. Clean it up here. It will be true for any pair of media. It can be rarer to denser medium, or it can be denser to rarer medium. Okay? So what does that law exactly mean? It is better written as sine I by sine R is equals to constant. That constant is replaced by a symbol n to 1. Just a caution here, if you are a CBSE student, yes, the book is following n to 1, nothing to worry. If you are an ICSE student, I would like to write it for them. The book follows the symbol mu to 1. Okay, this is the way of writing in the ICSE textbooks. where whatever you're writing, the meanings of the symbols will be exactly the same. Where n to 1, or you say mu to 1, means you're calculating something called as refractive index of the medium 2 with respect to medium 1. That's it. That is the way to read this symbol. That is the way to make use of that numbers 2 and 1. So you are actually calculating what we call as a refractive index or index of refraction of medium 2, whoever it is, with respect to medium 1. So it also lets you know that with respect to is super important. So the index of refraction is a relative number. And this index of refraction is a ratio of two angles. So you can easily see that we are left with no units. So index of refraction is a pure number. Alright. So here I am calculating the index of refraction for the second medium with respect to the first medium. But if you ask me immediately, sir, what is the index of refraction for the first medium with respect to the second medium? Then the answer is absolutely simple. It comes from what we call as the principle of reversibility of light. The principle of reversibility of light is very, very simple to state. What it says is that light always retraces its own path. So let me just show you in this ray diagram. Just imagine the refracted ray in whichever direction is going in the second medium. If I place a plane mirror on its pathway so that the refracted ray actually makes an angle of 90 degrees with the refracted ray, that is a case of normal incidence. Plane mirror, as we have already learned about it, it is going to make the ray to bounce back along the same path. So as it bounces back along the same path, now it travels back from medium 2, hits the interface. Now it has to go to the rarer medium, so the speed of light increases. So it will be now bending away from the normal, exactly along the same path in which it exactly came through. So you'll find this happening. So if you want refractive index of medium 1 with respect to 2, you write n12, or you could have also written mu 1 2, refractive index of 1 with respect to medium 2. So the formula will be, yeah, you got it right. That will be sine of r by sine of I. That's it. As simple as that. So if you are calculating the refractive index of 2 with 1, sine I by sine r. If you are calculating refractive index of 1 with respect to 2, by principle of reversibility of light, it should be sine r by sine I. So you can easily see it. If I just rub off this space, you'll see that sine I by sine r, which gives me n to 1, whereas sine r by sine I gives me n12. So therefore, if I just multiply n12 with respect to n21, if I just multiply these two refractive indices, then what we get is, I wrote n12 here, so sine r by sine I multiplied by sine I by sine r, and you lose everything and you're left with 1. So it says that n21 is always the reciprocal of n12. Or you can also see it the other way. The refractive indices of both the pair of media, the product of them, should be always equal to 1. Okay, that's extremely important. So once you calculate the refractive index of medium 2 with respect to medium 1, you need not do that sine r by sine I. Simply take the reciprocal of your answer, you get n12 for it. Or for the case, the other one around. I hope I'm very, very clear. Alright, please note it down and just excuse me. So now we would like to move forward with this concept, and as you can clearly see that the factor, what is this refractive index? What is this refractive index talking about? If this is your medium 1 or if this is your medium 2, some students tend to get confused which one is exactly medium 1 or medium 2. My dear, the idea is very simple. The ray could have come from bottom to up, top to bottom, whatever the case, you did not worry. The ray of light, for example, the ray of light is coming something like this. That's it. So in whichever medium you will have your incident ray present, take it as medium 1. Just continue drawing its original intended straight path. Never forget to put in the normal passing right through the point of incidence, and depending upon who is optically denser or who has higher refractive index. That's very, very important now. Optical density, the measure of the optical density of the medium is given by a pure number, which is always relative with respect to the other medium. That number is called as refractive index of the media. So in this case, if I say if medium 2 is optically denser, I mean to say medium 2 has higher refractive index in comparison to medium 1, then the ray of light should be going this way. Simple. So in whichever media you have your refracted ray, it becomes your medium 2. So angles, always get them right. This is I, this is your R. Is that clear? Alright. So that is very, very clear. Now, we could have said, not in terms of angles, but I could have described this entire scenario in terms of the speed of light. So refractive index can be also related to the relative speed of light in both the mediums. So if I say the speed of light in the first medium, whatever it was coming at a speed of suppose v1 meters per second, and as soon as it enters into medium 2, the speed of light suppose decreases because it is optically denser. So let us say the speed has become v2 meters per second. So I did not tell you, you can easily see that v1 is greater than v2 in such a case, or you can easily see that the measure of angle I is also greater than measure of angle R. It would be exactly opposite if you just take the situation opposite. If the ray would have been going from medium 2 to medium 1, the answers would have gone exactly the opposite, right? In such a case, if the speed of light is v1 in the first and v2 in the second, still I could have calculated the refractive index of the second media with respect to the first. Then we do n21 is equals to the speed of light in first medium by speed of light in second medium. This is the definition of refractive index with respect to the speeds of light. So in symbolic notation, n21 could be easily written as v1 meters per second by v2 meters per second. I bother to write the units to let you know and make it exactly fixed up that the units actually get cancelled off. You're left with speed by speed. A number by number is equal to a pure number. So hence n21 can be written as v1 by v2. This is one way of writing the refractive index of the second medium with respect to the first medium. So by principle of reversibility of light, it is not a big surprise anymore that if I have to really write n12, the refractive index of first medium with respect to the second medium, then I should have been doing the opposite, v2 by v1. So here, my dear students, if you're just not careful enough, you may just tend to get confused up in the exams. All right, so we'll do it something like 2 1 1 2 1 2 2 1 in terms of speed of light. In case you don't know the angles of incidence and angles of refraction, but you know the speeds of light in both the media, still you could have calculated the index of refraction of both the media very comfortably. So many have already discovered that n1 2 product n2 1 comes out to be exactly 1. So always that's a very important criteria, that the product of the index of refraction of both the pair of media is always equal to 1. Okay, so that's it. Please note it down. So now we have absolute clarity. Okay, I hope so. I'm very clear. The refractive index of medium 2 with respect to medium 1 could have been calculated as sine angle of incidence by sine angle of refraction, or could have been also calculated as speed of light in one by speed of light in the second medium. All right, the other one is exactly reciprocal of the first answer. All right, so you have these double ways, one in terms of angles, one in terms of the speeds of light. Make it sure still I bother to write in bold alphabets. It doesn't have any units. Okay, refractive index is only a relative number, doesn't carry any units. All right, good. Now there's a simple new terminology. It is called as absolute refractive index. So what is absolute refractive index? Absolute refractive index is the terminology which is utilized in our discussion when you are measuring the refractive index of any transparent medium with respect to air or vacuum chosen as the first medium. So air or vacuum chosen as the first medium, the other transparent medium becomes your second medium. In such a case, the ray of light traveling from air or vacuum and directly getting into the other transparent medium, definitely the other medium is going to be optically denser. So the speed of light in that medium is going to definitely decrease. So it will be shown as if it is bending towards the normal. This is your angle of refraction, this is your angle of incidence. There is no other better media than vacuum or air to be called as the ultimate transparent mediums. So any other medium will be automatically optically denser. So in such a case, if I want to find the refractive index of this medium, I just neglect to write with respect to air or vacuum. It is automatically understood the other medium is air or vacuum. So Nm is equals to the speed of light in air or vacuum by the speed of light in the medium. Okay, so symbolically it is written as Nm is equals to C by Vm, where C is the symbol for velocity or speed of light in vacuum or air, and that has a fixed number. It's a universal constant, and that number rounds off to 3 into 10 to the power 8 meters per second divided by Vm. So this is your ready-made formula for absolute refractive index. My dear, even if this value is not mentioned in your question, you're always free to use this for your calculation for speed of light in air or vacuum only. For any other medium, the speed of light will be decreasing. That is this Vm in the denominator. So you can also see from this relation, the speed of light in any medium can be safely written as C by Nm. The velocity of light in vacuum by its refractive index is equals to the speed of light in that medium. I hope I'm very clear. This is called as absolute refractive index. Great? Feeling good? That's great. Okay, let's move on. Let's move on to a very specialized condition of Snell's law, where it says that it is only true for a pair of media and for a given color of light. So what did exactly Snell's law mean? What is the exact meaning of Snell's law? Since now we know all the varieties of calculation, what exactly it means now? All right? It says that if suppose three friends are experimenting with different transparent media, and one has chosen air with respect to water, the other has chosen air with respect to kerosene, the other has chosen air with respect to alcohol. So you can easily see that all have chosen the first media to be the same. The second media has changed. All have also chosen the same colored light for their experiment. Let us just take it's red colored light. And all have also maintained the same angle of incidence. Let us just suppose is around 30 degrees. So all have chosen a red colored light. All have chosen the angle of incidence to be 30 degrees. And now they begin to do their experiment and they want to find out the refractive index of the second media with respect to air. The point is, the ray of light in all the three cases would not be going definitely straight for sure. And in all these cases it would be bending towards the normal. It means that the speed of light would be reducing in the second media, whatever the three friends have chosen. But will it be bending by equal amounts in all the three media? If you observe the physical state of the second media, it's exactly the same. Liquids. Physical media of the first medium chosen, gaseous medium. So do you think the angle of refraction will be the same in all the three cases? Will the speed of light decrease by the same factor in all the three cases? Think about it. I think you got it right. The answer is not going to be the same. Here you find some kind of angle of refraction, here you find some kind of angle of refraction, here you find some other angle of refraction. So if all these three friends do the calculation of sine I by sine R, definitely even though I is same, their R won't be the same, and hence the ratio will not be found to be constant. That is very important to be understood. So it says that sine I by sine R always is constant for a fixed pair of media, not for different pair of media. That is what my purpose was, to make you understand. But at the same time it says that this constant, what we call as refractive index of the second media with respect to the first, will be constant. That it also depends upon the other factor, that is called the color of light. If one might have chosen red, the other might have chosen blue colored light, the other might have chosen suppose green or yellow colored light, and even if they have chosen air water, air water, air water with same angle of incidence, still the answer would not have been exactly the same. So color of light is extremely crucial, and that is characterized in technical language by the wavelength of the radiation symbolized by the Greek alphabet lambda. All right. Now you may be thinking about the third possible doubt. If I take air, water, air, water, air, water, and I maintain the same colored light but change the angle of incidence, one chooses 30, the other chooses 40, the other chooses 50 degrees, will I find sine I by sine R to be constant? The answer is absolutely yes. That's it. Sine I by sine R, the refractive index of the pair of media, is completely independent of the angle of incidence. It only depends upon the nature of the media, that is the pair of media in concern, and it depends upon the wavelength of the light. That is the color of the light chosen for the experiment. Alright? Make it sure, my dear, wavelength lambda multiplied by the frequency of the radiation gives us the velocity of light. So whenever light travels from one transparent medium to another, we have been continuously saying the speed of light decreases. But when the speed of light decreases, do not misunderstand that the frequency also changes. The frequency of the radiation chosen for the experiment will always remain to be constant. What changes is the wavelength, not the frequency. Frequency is decided by the source of production of light. So the source itself will be deciding what should be the frequency of radiation, and that is completely unaffected as light passes from one media into another. Is that clear? Please check it out. Okay? Please, come on. So now I'm going to ask a simple question. After knowing how to calculate refractive index in terms of angles as well as speed of light, now let me put this question forward. Suppose we are talking about air-water medium, a ray of light coming through air at a speed of c meters per second enters into water medium. So definitely water is optically denser. So the speed of light is going to decrease in water medium. So let us denote the speed of light in water as VW meters per second. That's it. On the other hand, there is another scenario with respect to air where I measure the optical density of glass. So here also let us say the ray of light traveling at c meters per second in air gets into the glass medium, definitely can't go straight, bends and slows down to a speed of Vg meters per second. I hope my question is clear. Okay. So if you want to find out the speeds, if you want to find the refractive index, you have all the tools ready for you. But my question is, find the refractive index of glass with respect to water. Or for that matter, I could have also asked you, find the refractive index of water with respect to the glass. Anything would have been all right. So in such a situation, instead of really getting puzzled out, just stay calm with your concepts, be clear with your concepts, and get it done. My suggestion to the students who are learning for the first time all these new concepts, just treat this question as in your numbers. Let us call G as 2, W as 1. So it becomes in my mind, the question is actually asking me n to 1. And we are describing the entire situation in terms of speeds of light. So I will be not bothering about the Snell's law in terms of angles. So n to 1 in terms of speed of light, and remember it is V1 by V2. So for this formula where I have replaced 2 with G and 1 with W, then what I should get? 1 is W, so 1 is on the top, so I should be getting VW by VG. So this should be my target. Do I know what is VW? Do I know what is VG? Not directly, but we can find it. Yes. So we know from the first scenario that absolute refractive index of water NW could have been written as C by VW, which would have given me VW is equals to C by NW, provided you know what is NW. So let us call it as equation 1. And similarly for the scenario number 2, you could have written NG, absolute refractive index of glass, is C by VG, or VG could have been written as C by NG. Let us call this as equation number 2. Here we go. You have VW, you have VG. Great. Put that into the equation. Hence, NGW is equals to, what is VW? C by NW by C by NG. After substitution, you'll get to a very beautiful simple formula that it could have been written as NG by NW. So it means that if you know the absolute refractive index of the two different transparent medias, then you could have happily calculated the refractive index of glass with respect to water. Or even if I would have asked you NWG, the answer would have been NW by NG. That's it. My dear, it's all about generalization, clarity in your hand. So it means that N21 can be written as N2 by N1, or you mean to say N12 can be written as N1 by N2. Both are absolutely correct. Hope you got it right. All right. Now let's move forward to another very important question. Note it down. Yes. Moving forward to the next question, we have discussed enough of the concept of refractive index in this class. So let me get you to the ultimate thing. What did you understand? So if you look into the textbook table, there are a lot of absolute refractive indices printed for various transparent medium. So if I say refractive index of diamond, which is known to be the most optically denser, is actually around 2.42. Right? Sorry. Excuse me. So if that is the number 2.42 for diamond, which is called as the absolute refractive index for it, what does that number exactly say about diamond? Is it some kind of an angle or a degree? Has it to do something with the speed of light or something like that? Yes. If you understand that number, you understand everything. So what it is trying to tell you is, let us picturize it. If air and diamond are considered as two different transparent media, and you just visualize light rays passing from air into diamond, then definitely diamond would be optically denser. So it bends and speed of light decreases. So the speed of light initially was c. Now let us say it is around Vd. So if I ask you to calculate the absolute refractive index of diamond, then Nd would be written as c by Vd. So what it says is that if I put C and Vd values, then C by Vd values after calculation comes out to be 2.42. That is the meaning of that. That is how you get that number 2.42. So from here, let us generalize and see that the speed of light in diamond could have been written as C by 2.42. What it means? What does that mean mathematically? It means that the speed of light in diamond decreases or reduces by 2.42 times. 2.42 times in comparison to the speed of light in vacuum, which is well known to us as 3 into 10 to the power 8 meters per second. So in comparison to that speed, the speed of light in diamond has reduced. That is what we have been saying again and again. It has reduced by how many times? What is the factor of reduction in the speed of light? The answer is, it is reduced by 2.42 times. Hope very clear. Alright? Please note it down. Now, let's get to the most important part of this class. What you have been waiting for. Proof of Snell's Law. The proof of Snell's Law. Many students keep on this question in their head for a long period of time. Why there is suddenly the trigonometric ratio sin I by sin r chosen by Willebrord Snell'S to define this number called as refractive index. Okay, here I will use a non-calculus method. There are various methods based upon calculus also. So the simpler method to understand the derivation of this relation is, let us imagine an interface separating two media. This is our medium 1, this is medium 2. Okay. Now let us say a ray of light starts its journey from point P obliquely and travels this way out. And this is the normal at the interface. At the same time, along with the point P, there is another ray of light parallelly starts its journey and comes and strikes the surface. Let us call this as Q. So this would be the normal for this ray of light. Since both the rays are absolutely parallel to each other, both make the same angle of incidence. Is that clear? Alright. Now if you observe it geometrically very closely, by the time the ray of light P strikes the interface at O, the ray of light Q does not hit the interface at the same time. So you can clearly see that by drawing a perpendicular line onto that ray of light Q, and you can clearly see this. There is a gap. So let us say this point is around R, this is S. So it means that from the diagram, the ray of light P traveling from P and striking at O, in the same time the ray of light Q has only reached to the point of R, so still it is lagging behind by a distance of Rs to be covered in a time of t seconds. That is the distance which will be pending around. Alright. So by the time the ray of light Q covers this distance Rs in a time of t seconds, in the same time, what about the ray of light P? Definitely, it would have moved into the second medium by changing its direction and by reducing its own speed. So let us say that the ray of light P in the medium 2 might have traveled some bit of distance, and let us say that it has reached to a point called M over here. So this angle, as you all know, this is your angle of refraction, same angles over there. So if this is the distance, let me connect, and using geometry of the angles, we can easily find out what exactly is happening around. Alright, so if this is your I, this is your 90, and if this is your I2, then this has to be 90 minus I, listen to me, then this also has to be your I, because the sum of the angles of triangle is 180 degrees. If this is R, then this angle has to be 90 minus R, so this is left with R. That's it. After you have cracked that part, not a big issue at all, so let us do it. In the triangle ORS, let me write down what is sine of I. I find sine of I is perpendicular by hypotenuse, so RS by OS. RS by OS. So you find sine of I is equals to, what is RS? It is a distance. It's a distance traveled by the light ray in time t seconds. So if I say the speed was v1 in the first medium, then the distance should be equal to v1 into t. So v1 t. And let us say this OS be equal to something called x. So let me put over here x. It's a supposition, all right? Now sine of I is equals to, what is v1? What is v1? V1 could have been written in the language of absolute refractive index as C by N1, medium 1. So in place of V1, I could have written C by N1 T by X, and hence you find N1 sine of I is Ct by X. Let us call it as equation number 1. Great? Okay. Hope I'm clear, my dear. So in the meanwhile, the ray of light P also has moved into medium 2, traveling and covering a distance of OM. So definitely in this medium the speed of light might have reduced. So let us say the distance covered is V2T. So in the triangle, what is the new triangle we have? OSM. OSM, yeah, sounding good. So I will write the sine of R. The sine of R has to be equal to perpendicular by the hypotenuse OM by OS. Everything good? Right. Then sine of R should be, what is OM? Yeah, that is the distance of V to T. What is OS? Supposition X. Now what is V2 in the second medium? So it's the second medium, so I could have safely written C by N2 using the concept of absolute refractive index. So you write Ct by N2 into X. So hence we can write, I think I have space over here, N2 sine R should be Ct by X. Let us call this as equation number 2. So look into the equation number 1 and look into equation number 2 and you clearly go bingo, right? The right hand sides are equal, so from 1 and 2 you hit the button. N1 sine I is equals to N2 sine R. Rearrange it according to your necessity. Sine I by sine R is N2 by N1, or which could have been also written as N21. Hence, your doubts are cleared. That's what we have for Snell's law. Why there is a sign ratio to define the refractive index of an area. Hope I'm very clear. So before leaving, ending up today's class, let me just rewind quickly what we have learned so far and how many tools you have to solve N21. N21 can be solved as sine I by sine R in terms of angles. It could have been solved as speed of light in the first by speed of light in the second, or it could have been also solved as the ratio of absolute refractive index of second by the first. This is also right, this is also right, this is also right. Hope my dear students, I am very clear with the concept of Snell's law, the proof, the refractive index. Hope you enjoyed learning physics. Physics is always fun. Keep enjoying, take care of your health, stay fit, stay happy. See you again in my next class. Do not forget to join SMR Online Physics. Bye, take care.